Hello, everyone. Today my topic is first example, researching new attack interface on iOS and macOS. This is the agenda of our topic. We will first introduce the overview of our solution. Then we will detail how to automatically generate the attack interface through static and dynamic analysis. What's more, we will also introduce our Diff methodology to find the newly attack service when system update. Finally, we will talk about the automatic fuzzing solution and the vulnerabilities we found. My name is Lilang Wu, and I have 4 years of security experience and is a member of Mobile Advanced Threat Research Team of Trend Micro, and now focus on macOS, iOS vulnerability discovery, and malware hunting. And latest Moony.
Hello, everyone. I'm Moony. We have about 9 years security experience, mainly focused on the Mac and Android iOS vulnerability hunt and exploit. And also, I have developed some kinds of sandbox projects.
Now let's talk about our automatic fuzzing solution. Our solution has 3 main components, including automatic static reverse engineering, dynamic analysis, and fuzzing solution module. Static reversing engineering is responsible for analyze the main attack service in kernel and kernel extension automatically, and output them into a vector. Dynamic analysis will make up and perfect this newly attacked service vector. Finally, this attack service will input into our passive fuzzing tool in order to find the potential vulnerabilities. Now I will introduce how to analyze the kernel and kernel extension attack interfaces statically and automatically. Think about in the world. I think the factory, military base, big city, or other critical places may be the most possible for enemy to attack. So, for Apple system, there are also many critical places which may be vulnerable, such as XPC service, MIG system, kernel, and kernel extensions. Traditionally, for example, kernel extensions, we should manually analyze the critical functions using ADA or other reversing tools to get potential interfaces. It's trivial and time-consuming. So, next we will introduce an automatic analysis method. This figure shows our reverse engineering solution. First, we will analyze the kernel and the kernel extension to get all the attack interfaces from a newly released version and generate UserClient vector, external method interfaces vector, and so on. The second step is to diff the XNU projects and kernel extensions between 2 neighboring versions, which can get the update functions entry list. The third step is to filter out those entry functions which cannot access to from user space and save those remaining. And last, we will collect those remaining interfaces and save them into our fuzzing curves. Next, we will introduce the kernel extension interfaces vector automatic generate solution. It may introduce 4 steps. We first analyze all the drivers and get all classes in inheritance relationship. Then refine the method names based on inherit mechanism. Thirdly, we will automatically analyze the user clients in each extensions and their connection type. Finally, we all know that there are many external methods for each user client, so we will locate them and pass related content. In the allocate mechanism, OS meta class function messages manage runtime type information for libkernel and allocate classes. It is called then at the binary level with 4 instead of 3 parameters. The first one contains a pointer to the meta class, which will be constructed. The second one is its name. The third one is its parent meta class instance. And the fourth one is its size. So through this function, we can find all classes inheritance relationship. As we all know that string symbols was stripped in release version firmware, Apple firmware. So it will refine it should refine the method names for each OS object classes, including instant method table and meta method table. Through the inherit mechanism, many method names can be refined from its parents. And for user client analysis, the key function is also its new user client function. This function responsible create a connection for a non-kernel client based on certain type. Right finger shows the graphic accelerator new user client function, which can refine some strings. IOUserClient is also a subclass of IOService, which provides a basic for communication between client applications and allocate objects. This finger shows the process how to execute an external method, and all the external methods are implemented within these functions. So, for researchers, it is necessary to analyze this function to get the driver's external methods. After we got the analysis flow and analysis point, all we need to do is to implement the automation process and get the related attack service vector. For example, we should get this kind of connection type user client tuple for user client analysis for as shown in above finger. And external method display table like below finger shows, for example, for external method analysis. For KASAN tuple, the automation methodology can be following. First, we should locate the new user client function address in each driver. Next, we should analyze the assembly instruction to enumerate the connection types, as well as the corresponding user client. Generally, the initialization of each user client corresponding to different types is controlled by if clause or switch clause when it has multi-connection types. So, assembly instructions analysis is must. For external methods, generally subservice will define it in the external method override function, and the display table then usually is a static local or global constant array. If subservice not override external method function, it will be defined in the get target and method for index or get async target and method for index function. And the dispatch structure will be also a little different. Even though any one of these two implementation is Gracefully, which can easy to analyze. For this kind of Graceful implementation, we can firstly locate the starting address of each constant array in symbol table, and then pass the content according to this these two kind of structure. So the important is to how to locate the address of this constant array. However, not all drivers use that Graceful implementation. Actually, most of them use switch clause or if clause to control the execution of external methods. So it will be the same situation with the new user client function analysis, which both need to analyze the assembly instructions. Next, we will introduce how to locate the address of those key local and global constant array firstly, and then introduce our assembly instruction analysis methods. Actually, the symbols of local and global constant arrays are saved into symbol table section. So we can search those symbols which start with NNZ and ZN, ZZN and ZN. For example, the finger below shows the array symbols of our frame buffer user client and our HID user client. So it will be easy for us to get this kind of external method dispatches automatically. However, for assembly instruction analysis, there have been some reverse engineering framework available, such as Anger and Mizam. This kind of frameworks both disassembly binary code, construct assembly CFG, and emulate instruction execution using GIT. But it also has many disadvantages, such as it needs to map multi-code into virtual memory in order to keep one function run smoothly due to the complexity of operating system. What's more, for getting an external method dispatch table as mentioned above, it is difficult to construct different conditions automatically to support all the passes. However, if not use this binary analysis framework, we should construct instruction simulator by ourselves and construct a kernel analysis agent which used to analyze metro film and implement virtual memory operation. We think about what we want. We only want to pass the connection type and or selector in the if condition clause or switch case clause, and get corresponding user client or external method. So we do not need to simulate all of instructions operation. We can only simulate those instructions within if clause or case clause, and only care about certain register data flow. Therefore, we can customize a kernel extension analysis agent, use Anger or Mizam to generate CFG or CG, and customize an instruction emulator, which can eventually help us to generate a tank service automatically. Now we will show you our practice about how to customize kernel extension analysis agent. Our analysis agent, including implement metro film parser handler, which could pass key sections and segments. Implement the virtual address and the film address operation, and also implement the memory operation. Here is our implementation. The first three functions are used to search the virtual and film address for each segment and section. Next four functions are used to get memory content or string for a given address. The following two functions implement the switch from each other for virtual address and film address. This class is responsible for map a metro film into a class and pass all sections information in order to provide basic information for our agent. Actually, there have already some this kind of open source libraries, and our analysis agent is also implemented based on them. Last, we defined the OS meta class that used to save all the detailed information when online each user client and external methods. Here we can see that we save the details information about analyzed classes, the address of many key functions, and whether it can be connected from user space, and its connection type is yes. In other words, you can search any details information from this class after each meta class analysis finished. For CFG generation, we use Mesm. This tool is open source, and it has its own usage documents. So here we will not introduce it again. This is an example. The new user client function of Apple HID agent classes. It has three connection types. After analysis, Mesm can construct the control overflow graph and right finger show. As mentioned before, we can only care about the certain register's data flow. In this example is R14D register. Actually, this register is pointing to the connection type register, which is the fourth parameter of new user client function. For external method, it's the same. After get this branch using CFG, all we need to do is to analyze them to get the related user client information or external method information. Next, we will introduce our customer instruction emulator implementation for analyzing each branch. As mentioned before, we only analyze those key functions. Therefore, it will contains a small part of instruction we need to emulate it. So it will reduce the difficulty and complexity. Here we list some instructions we emulated, such as ADIP on ARM platform, and LEA mode call instructions for x64 platform. These two pictures show some register operation emulation, such as get the immediately value offset register name from instructions. Eventually, our tool can output the analysis result into a database for fuzzing tool to query. This result including the tuples of service name and their connection type, and dispatch tables which contains the selectors and corresponding parameter size constriction. Next, we will introduce the Kernel Interfaces automatic analysis. Due to kernel part is open source, so it will be easier to analyze them than execution part. We can simply to search these films and pass the related interfaces. Next, we will introduce our interfaces diff analysis solution in order to get the newly changed attack surface. For kernel, we firstly pass and diff those films we just mentioned in code screen for getting the newly interfaces. These interfaces include the newly added ones and arguments changed ones. Alternatively, corresponding information can also be get from the kernel binary analysis tool like Joker. Secondly, we diff all the film except some noise, like unit test films in the XNU projects, and tag those changed or newly added films. Thirdly, make statistics for changed or newly added function names within those films. Fourthly, construct the calling sequence for the changed functions and get their entry functions. Finally, check these entry functions if they exist in about interface vector, and save the code graphs if yes, which are the newly attacked service in kernel we should pay attention to. We recommend open source visual diff and mod tool, MELD. This finger shows is this finger below is the diff results we get it by MELD. Actually, it's the patch of CVE 2018 4243. Therefore, we customize its diff interface and add the function name recognition module in order to automatically output the newly added or changed function names. For construct the calling sequence for the changed functions, we implement a tool pdiff based on ILR script. A good news for us is that the kernel is open source and nearly no strips the strings, so it is friendly for us to construct the code graph. The right finger is the entry function list we got from pdiff, which can touch this changed function through user space. But it's a little different. Kernel extensions are closed sourced, so we can't use MELD to diff the source code films. Here we develop a ILR Pro script based on bdiff plugin, which can easily recognize the similarity between two functions, and then using pdiff to output their entry functions. However, there exists some problem in the implementation. One is the string. The strings in kernel extensions are heavily stripped. And another is the function calls are most companies using class objects pointer plus the method offset. So it's difficult for us to construct CFG and CG. Therefore, there will be multi functions we cannot analyze. So we should using dynamic analysis for us to make up this part. Next, we will let Moony to introduce the dynamic analysis.
Hello. Actually, we have introduced how to find the attack interface from the static view, and now we will get another view to finding the attacking service from dynamic analysis view. So As we have mentioned before, the key methodology for dynamic analysis is to get the runtime context of a attack interfaces API so as to have trigger, fuzz, or even reproduce the potential vulnerability. As our best practice, we would choose Frida to control and trace user mode context and Dtrace, which is embedded to the macOS kernel to trace the kernel counterpart. As the manual affiliation, the debugging where LLDB, both the user mode and kernel mode, is also reasonable. So the kernel above is the basic comparison summary among all the kinds of dynamic analysis tools. Where's the trick? 鼠标吗？哦。Okay. Let's introduce the Frida hook in user mode hook. The Frida may be one of the most popular dynamic instrumentation toolkit on many platforms, including the macOS and iOS. One of the most cool advantages is that it allows the researcher to pick and control every functions or APIs using well-documented JavaScript API, which including the pre and post event handling. Typically, the retrieved runtime information, including the call stack backtrace, thread context, return value, and any other you can define it. As you can see from the graph, the right side is the Frida controller, which is wrapped in Python, and the left part is in the controlled part. The most part is with the Frida server, which is with the root privilege. So this Frida server can attach any process of which you are interested in, and also it will inject the Frida server .arm.devlib to any kind of target processes, so that it can hook any API or functions with a script of JavaScript, and this kind of scripts can be delivered from the USB or Wi-Fi or any kind of transaction from the Frida controller. So you can define your own kind of JavaScript to hook any kind of API classification. For example, the allocate, system call, file system, network, and the other part. Take the XPC connections and the message API. For example, this is a typical API to communication between two different kinds of processes. For example, we can hook this API. The name is XPC connections message, and we can also extract the arguments in the artifact part. The name of connection and the value of 1645. The argument sequence number is 0. And also we can get the concrete value, such as the connection value, the connection name, and the connection process ID, process name, and also this is a whole picture we have got from the iOS runtime environment using the Frida hook. This is a typical scenario when you install an iOS profile from the web browser, for example, Safari. You can install any kind of profile from the web server, and this profile can be controlled to control your iOS devices. For example, set up the APN or VPN proxy for your iOS devices. And you can see that we have also classified all the kinds of processes which is related to the iOS profile installation process. And the left part is mobile with the mobile privilege, which is lower privilege, and the middle part is also the mobile privilege, but it can directly work with the process the profile file, and the right part is all the devices such as the lockdown daemon or launch daemon with which is in the root privilege, and all these kind of processes with different kind of privilege that can be hooked or attached by Frida. Also, we have hooked the communication APIs such as XP6 and message, and we can get the exactly path and concrete values of the API. And we can get the workflow and the relationship from different kind of processes, as you can. Another kind of dynamic trace analysis is the Dtrace, which is embedded to the OSX kernel. Dtrace is one of the best tracing design with the high performance and usability in Unix-like system, including the OSX. Badly, Dtrace is not officially supported on iOS real devices. So, as you can see from the architecture above, the Dtrace implemented in the Dtrace provider in the lower part in the kernel, which supported different kinds of sensors, or which we call it providers in the kernel, such as system information, VM information, and system call profile, and file system, and so forth. And in the user mode, it can receive and accept any kind of Dtrace file, which you can define the pre and post handling events in this kind of script. And also, you can get the results at runtime of the Dtrace. And this is Dtrace provides multiple probes embedded in the kernel with classified and system information, and FBT, SDT, and so forth. Which you can see from the graphic Dtrace /L command. The typical system call, including the allocate, match message, and the network, and the disk and the file operations are also covered by Dtrace probes. And what's more, Dtrace, the language in script, provides a fruitful API to intercept pre and post events. For example, the begin and end keywords related to the runtime process context. For example, the PID and process name, timestamp, file name, and the execution name, and so forth. And you can see the code pitches from the IO file probe. For example, you can get the exactly the file operation, including the PID, execution name, and arguments of file path, and so forth. But the drawback for the Dtrace is that it could not, it just can view the execution of the API execution, but it could not control or modify any kind of context values at runtime. So in this part, in the next part, we will introduce our automatic passive fuzzing solution. Here is the whole picture. As for the key methodology of fuzzing, we could like to touch more execution paths code coverage as possible as to catch the first spot of kernel crash by our fuzzing. So, as the first step of fuzzing is trying to generate a fruitful corpus about kernel interface APIs and call to the kernel from the user space agent. Besides the blind fuzzing, such as AFL-like, we recommend to utilize the normal program, which would have more chances to interact with the kernel as the agent. For example, when you're playing some 3D online games towards the OpenGL or graphic-related drivers, and the peripheral devices operations, such as when you connect to the Wi-Fi, Bluetooth, and manual amendment, so that a lot of real operations towards the low-level drivers could be attached to the kernel. So what we have done is to do some inline hook to the system calls to the checkpoint of the system calls from the user mode to the kernel mode. So a typical inline hook could include the allocate isIO-connect call method and allocate async method and allocate client trap, create mapping task in the kernel, which can copy the user mode buffer to the kernel, and also we can hook the copy IO, which is called directly by the driver. So once the data flow is transferred from the user mode agent from the user mode to the kernel, in our inline hook point, we can fuzz and tint the buffers which could be directly controlled by the user mode buffer. So this kind of tinted buffers could be delivered to the deeper code coverage of the kernel execution or the driver execution, so that we have a chance to crash the kernel with our tinted buffers. And what's more, this kind of buffer is only controlled or be controlled from the user mode. So we can make sure that this kind of crash could be reproduced from the user, but not just blind fuzz. And also we have introduced the kernel address centralizer in the memory related operations so that you can catch the operating the boundary or overflow checks on the spot. For example, we have embedded our kernel address centralizer in the global overflow or heap underflow, overflow, UF, invalid double free, and small free, and so that. So if any kinds of issues is happened to this kind of crash issue, we can get the kernel crash on the spot. And this is actually kernel address centralizer is one of the standard centralizers supported by popular operating system, including OSX, which help to catch the crash spot so as to identify the vulnerability root cause and reproduce it much more easily. So what's lucky is that the KASAN feature is officially supported in the XNU building. So you can build your own XNU kernel like this. In the left part, make SDK root, and you can configure the kernel configs with the KASAN keywords. And for our future plan, we can see that this color like fuzzing in the kernel mode. As we know, the runtime environment in the kernel would be complex. There would be existing many environment preparation or neutralization. For example, Open Correct service initializes the target devices and sends the correct match message ID before one special kernel API, such as alchemical method, could work properly. So why do not interception the kernel API at the proper time and the proper state and fuzz it like FL in kernel mode directly? This is one of the planning to implement the as well as caller fuzzing in kernel mode. And the other part is about the porting KASAN or K-memory centralizer for closed source drivers. So, because the officially KASAN mechanism is supported by the XNU kernel, which is open sourced. He will modify the source code of XNU to catch all kinds of memory allocation. For example, the K memory malloc, free, and any kind of memory reference or dereference. So maybe we could also porting this kind of memory or address centralizer to the closed source drivers, so we can extend our scope of fuzzing. Okay, the other part we will introduce the zero-day vulnerability we have found by our fuzzing solutions.
Now, let me introduce the vulnerabilities we found before. This is one vulnerability we found in AMD frame buffer driver. This driver is used to process the graphic data and can be accessed to by Windows Server process. The vulnerable function is EXT, get pixel information method, which is one of the IO frame buffer user client external methods. And the selector is 1. The method takes 3 scalar inputs data, which are display mode, dips, and a picture, and return the pixel information in the end. This is the debug information around the crash point, and found that the register of IDI is a very big value. However, before the crash point, this function indeed check the dips value boundary in the if clause, which restricted no bigger than 2. But the vulnerable point is that it transfers unsigned int to a signed int before check. So we can set the highest bit of unsigned int to 1 and transfer it to a signed value, which will be a negative. So it can bypass this check. In the crash point, we can see that due to RDI register is a big value. So RCX register plus RDI register multi-at will be an invalid address. So it will cause a page default error. However, if we craft a good value, maybe we can use the foreign string copy function to leak some kernel information. This vulnerability is found in AMD Radeon X4000 driver, and the vulnerable function is AMD Accelerator resource in initialize method. AMD Accelerator resource class is used to process the graphic accelerator resources information for 3D rendering. This vulnerability can be triggered from user space by AMD Accelerator service. And the external method select is 0, whose function name is S new resources with connection type 6. This function accepts a struct input buffer whose size is 2424. So there must be multi-checks within this function. If any one bit is not checked properly, it may be result vulnerability. And indeed, we found another vulnerability in this function and already submitted to Apple. In this vulnerability, as shown in above figure, the register of RAX is in the place A is the address of the buffer which created from our malloc function. R15 register is in the place B is point to the structure input buffer we mentioned before, which can controlled by user mode. And ECX register is equal to R15 to plus 0xF8, which point to a value offset 62 dV from structure input. From place C and place F, we can see that it actually used to control the total copy times from structure buffer content to our malloc buffer. And from place D and place E, we can see that RDX register is used to control the copy size for each copy. Place G is the copy operation which copy contents from structure input to our malloc buffer. So obviously, RCX value is get from user space in class B and have no any checks. Therefore, an out of boundary read will be happy if it is a big value. This is an overflow bug found in our USB family driver. And the vulnerable function is low latency prepare buffer methods. This method can be called from user space with select 17 and accepts a scalar input buffer with size 7. This is the crash frame. This function is used to create a memory buffer with memory descriptor for that buffer. The capacity parameter is the number of bits to allocate. Here we can see that the capacity value is 0xFFF. Obviously, it's an invalid value for this function. This is the debug information. The last LLDB instruction is to read the memory from the start address of input scalar buffer, which can input from user space. We can clearly see that the invalid value is the third value in the scalar buffer. So we can control the value of capacity from user space. This bug is found in Intel Accelerator driver, and the vulnerable function is Intel Accelerator new GTT from method. This function may be accessed to during connecting the user client with type 6. Left finger is the pseudocode snap of new GTT function. We can see that it uses look for GPU access function to get the accelerator system memory address and set it to V8 in the place A. And in place B, memory copy function use V8 and the destination address for copy connected to it. The right finger is the pseudo code snap or look for GPU access function. It obviously shows that it not always return a valid address. Therefore, it like a check for the value of V8 and resulting zero page write back when using memory copy. This is a divided zero bug found in AMD Radeon X4000 driver. The vulnerable function can be triggered using RO Accelerator command queue service with selector 1, whose function name is submit command buffers, and its connection type is 9. Our accelerator command queue is used to process the graphic accelerator command information for 3D rendering. When AMD driver processes these commands, it will prepare the AMD accelerator resources first. And this vulnerable function is responsible to optimize this resource buffer. This is the assembly code snap of this vulnerable function. R20D register is initialized with 0 in place A, and it will be assigned a new value within the omitted code if meets some condition. But that is not sure. Therefore, it will be result in a divided zero bug in place B. That's all. This is the tools we mentioned before, which generate the attack service automatically. We open source in this link. However, this is old version, and I will upload the newest one later. Thank you.